It's a pleasure to introduce Nick Early from the IAS, and he'll be talking about planar kinematics from generalized Biadjoint amplitudes to generalized worldsheet and beyond.
Okay, well, I'd like to thank the organizers for organizing this conference and for the opportunity to speak here. Thanks a lot for the invitation. So this is, I'd like to first thank my collaborators, the team at Perimeter Institute. This is developing, starting from work we did in the past couple of years. Freddy Cacciazzo, Alfredo Guevara, Sebastian Mizero, and the rest of our team. And here are the, how do I get rid of that? There we go. Yeah, so let me begin. So a preface, just a quick overview. Let's discuss the background for the formalism of Cacciazzo, he, and Yuan for scattering amplitudes. Okay, so let's look at let's remark that the moduli space M0n then points on the Riemann sphere. Well, you can think of this in terms of the two planes in n space in the Grassmannian modulo the torus quotient. So in number two, so what did CHY do? They formulated scattering amplitudes as a Morse theoretic statement about M0n in the sense that you write down a particular log function, multi-parameter log function, find the critical points, and that allows you to, as proven by Dolan-Goddard in the case of the Biadjoint theory, that computes for you a large number of scattering amplitudes. So they proved it for several quantum field theories. Okay. So there are indications of a need to generalize this. So in light of point one, can the CHY formalism be generalized to K by N matrices modulo the torus quotient? And yes. So together with my collaborators, we introduced the generalized Biadjoint scalar amplitude modeled on certain planar compactifications of GKN. And Thomas, could you, I think there are some questions in the chat. Just let me, if you could keep an eye on that. I don't know what was being said, but please do.
Okay,
yeah.
I will keep an eye on the chat.
Yeah, please, interrupt, please, at any time with questions. I'm very happy to answer. So, okay. Okay, so first we'll review CHY and formalisms and CGM formalisms for the generalized Biadjoint scalar. And then in order to understand these, we'll look at a generalization of the type A root system, which has been very useful to understand the structure, the internal structure of these amplitudes. So we'll develop some new technology here. Okay. Okay, so just some notation quickly. Grassmannians, I'll just stick an R on the G to indicate the k-dimensional subspaces of Rn. Use a notation P subscript J for a Plücker coordinate, that is a maximal k by k minor of a k by n matrix, denoted by x of kn, the torus quotient of the Grassmannian. And the last bit of terminology notation we need is the parameters S lower subscript J1 to JK, or a subset. These are the parameters for the amplitude. Okay, so our amplitudes are rational functions of the SJs. So the indices are distinct and unordered. And they have to satisfy n linear relations that we'll see in a minute. So the kinematic space is the space of generalized Mandel-Stemm invariants which satisfy these n relations. Oh. So the space, yeah. Okay. So two parts today. First, we'll give the overview, and then more recent work. And along the way, we'll outline will give hints to some possible questions for future investigation. There's lots to do here. So welcome any questions at any time. Okay, so today we'll use combinatorics to study amplitudes. That's the main structure today. We'll introduce a, well, in the case of the Biadjoint amplitude, there is a certain polytope whose which serves as the model for this object. It's the issosahedron of that's the classical issosahedron. Okay, and so we're going to introduce a generalization, which we call the Worldsheet generalization of that, yeah. So it's a modification of the Biadjoint amplitude. It leads to that. Okay. Okay, so on the space xkn, we define a function, a potential function it is called, mathcal skn is a sum of logarithms of the minors, each weighted by a generalized Mandel-Stem invariant. Note that it's well defined. One can see that it's well defined, constant on the torus orbits because of the n relations on the generalized Mandel-Stem invariants. So what does the torus orbit do? Torus orbit scales each column separately. Okay, so define the K-Park-Taylor factor as follows. Fix a cyclic order on the set 1 through n, and take the product of all k by k minors whose columns are cyclic intervals. Now take the reciprocal of that. All right, so that will be the building block for the CHY, and in the case k equals 2, and CGM construction in the case k bigger than 2. We'll see on the next slide, I think, how that goes. Okay, so this is the formula as written in our paper. So in fact, this is slightly more general than the setup which we'll need, but this is as given. So given a pair of n cycles, alpha and beta, we multiply the Park-Taylor factors for the cyclic orders alpha and beta, and to take into account the torus quotient, we divide by a certain factor, which is the reduced Hessian determinant of skn. So it's reduced because yeah, for technical reasons you have to take you can't quite take the determinant, but for technical reasons you have to make a slight modification. Okay, and then you sum this object over the critical points of the potential function, and this, by a global residue theorem, is a rational function of the parameters, the generalized Mandel-Stem invariants Sj. Okay, so the case k equals 2 was introduced by CHY. Joel and Goddard proved that the Biadjoint amplitude computes the M2, and maybe we can put an alpha and beta there, computes the amplitude for the amplitude for the Biadjoint Lagrangian. The so-called Biadjoint Lagrangian, and we will calculate in the case 2,4, we'll calculate the amplitude exactly in a couple different ways. All right, so let's work it out in full. So here is the 2,4 amplitude. We have a sum of all 6 minors, and we'll take a set of coordinates on here, a parameterization, using cross ratios. So one can show that this simplifies to the following expression. U13 is the ratio of 2 over 2 minors, and U24 is also a cross ratio. Okay, so take this to be a 2-parameter of functions of U13. So if you take the derivative with respect to U13, calculate the critical point, where that equals 0, you find it's given by U13 is S23 over the sum of S12 and S23. Plugging that into now the torus quotient of the Riemannian, you can represent it by this following point. Okay, so it determines a torus orbit. Now let's evaluate the amplitude here. In the case K24, our large expression simplifies as follows when written in cross ratio, in the cross ratio parameterization. And you can see that, well, here is the, here you have the Hessian factor and the Park-Taylor factor. They become, in the projective form, they take on a slightly different formulation. And it comes out to a negative of the sum of the reciprocals of the two Mandel-Stem invariants in the potential function. There is a minus sign to match the CHY sign convention. Okay, so that's great. And so now well, we should say the CHY formula in this case will connect to stringy integrals. I think that's the next slide. Yes. So here's another derivation. Write it as an integral. If you use the coordinates U13 and U24, integrate over du13, and it simplifies to this rational function of gamma functions. You know, some convergence requirements. Now let's take the alpha prime expansion. So alpha prime is called the string tension, and you can see that the leading order term in alpha prime is the same rational function that we saw for M2n, M24, modulo the sign. Okay, and this was generalized in a paper by Arkani Hamed, he, and Lam to cover the case K bigger than 2 and various other more general situations. Okay, so now we'll continue our overview. We'll look at M2n in various settings, and we'll illustrate how to work with this combinatorially. And in particular, we'll connect to the root system of type A. Okay. So there's a very nice basis of linear functions on the kinematic space. And it's given as follows. Take a sum over all AB that are contained in an interval ij. Okay, so it in the case K equals 2, the planar basis, which we'll introduce, coincides with these sums over intervals. For k bigger than or equal to 3, it's a bit more subtle. And there, yeah, I mean, lots remains to be explored there. Okay, so first let us give some motivation. Okay, well, we've seen this. We'll see this a lot. And a Planar graph. So Planar graphs appear in many contexts. They capture deep properties of objects in the non-negative Riemannian, positoid polytopes, and hypersimplices. Okay, but always we fix a cyclic order, and I'd like to understand why the cyclic order, sort of another reason how we can understand why the cyclic order appears. Okay, so that's at least in the case of the kinematic space. Now this want to see how to motivate that. So the question I want to pose is, what if planarity were an emergent structure, that it emerged from some other object? So here, if you look at the kinematic space, Kn, then to write down a standard basis of linear functions on this space, there's a single object, a unified framework to give this, and that's the following. Take a collection of rays in the directions of the simple roots. So E1 minus E2, E2 minus E3, up to En minus E1. Okay, and you connect every n minus 2 of them in a cone. Okay, and that you can use this object to induce the sum of the poles for our amplitudes. So for the experts, we can integrate these in a certain way to get the rays in the positive tropical Grassmannian and the poles. And these are very special rays, very specific rays. They're called multisplits. And for a direct connection of Planar graphs, let me just point out that in 2019, the result was that there was a bijection between weakly separated collections and certain ways to arrange these blades on a convex polytope called the hypersimplex. Okay, so a natural question is, we'd like to use these to see what more can we say about the poles of MKN. I think that's a very interesting question. And I hope to discuss that. Please, if no, I think that very deserves attention. So here, let me explain this very quickly. The points, the internal vertices here are the vertices of the hypersimplex where each one of these blades is placed. So you put a blade on a vertex of the hypersimplex, and this induces a subdivision that cuts it into a bunch of pieces, just kind of like a triangulation. And if you put a condition on the cells in that triangulation, quasi-triangulation in the subdivision, then you get the bijection with weakly separated collections, and by result, from a while ago, these are in bijection with reduced flat graphs. Okay. Okay, here's the basis of the kinematic space. So it's given by, first we'll define n linear functions on an auxiliary space, Rn. So I have this kind of uniform increasing step function. And proposition is this function, if you take the min of these n guys, it changes slope exactly on the blade. Changes slope exactly on this configuration of sheets. Using the data of this function, evaluating it on this difference of vertices, evaluating on this point in space, and summing over all subsets. So this means that we're taking all k element subsets of the set 1 through n. We sum over all subsets, we get a point in the kinematics. We get a function on the kinematic space. And you can see that it was shown that these functions form a basis. They're linearly independent. Moreover, when your subset J is a cyclic interval, then the function is 0 due to the relations among the SIs. Okay, this is essentially a planar object. So that's the point. So here are just some quick illustrations. Here's the explicit formula as it comes out from the function, but it simplifies to just S12, S23, and 0. Maybe one more slide. And then I should pause for questions. Maybe I should pause for questions right now. Okay. Okay, so there's a formula. Remember, we had this sum over critical points, the definition for the biadjoint scalar, sum over critical points of the product of the part-Taylor factors with an additional normalization. Well, there's a way to express this that's totally combinatorial. So in this situation, I'm translating notation from results, I think Sebastian Mizera, and then ABHY. They formulated this, they proved this. It's as follows. You take a product of n minus 3 of the eta of the planar basis elements, and then you sum over all n minus 3 collections of pairs such that the two pairs are non-crossing. Now this means that I1J1 and I2J2 do not form this crossing pattern either this way or this way. So the indices have to be completely separated when you put them on a circle. Okay, so yeah, the terms are then in bijection with the triangulations of a polygon and the vertices of an isosahedron. Okay, so now let's we'll move briefly to the k equals 3 situation. Okay, we have so a priori we have this. We started with this rush just a sum over critical points. We have input 2 cyclic orders, and just by choosing specific kinematics and various cyclic orders, you can sort of unearth step by step the rational function. You can build it from scratch, and that's what we did. If you choose the parameters S, A, B, C to be large prime numbers, then you can reconstruct it in full. So a remark is that it's possible by substituting instead of a product of cyclic orders some other product of minors, then the output is a single rational function given here, which is, well, it does not appear in the usual formulation of the biadjoint scalar. So you can see that this is a fundamentally non-planar object. Okay. Yeah. Okay. So so look back at our for k equals 2, there's a compatibility rule on the poles that guarantees that every rational function has exactly n minus 3 denominators, homogeneous of n minus 3. Now the novel thing for k bigger than or equal to 3 is that it's no longer so uniform, no longer quite so uniform. You have a lot of poles, and these poles have linear relations among them. For example, in already at kn equals 3, 6, so we have 3 minus 1 times 6 minus 3 minus 1 equals 4. So anyway, we have 4 poles here, but we have 5 compatible here. Okay, and you know, what do? Well, that's a little bit weird, but well, so it is. And we see linear relations that you can find that the 2 poles, the denominator here, they satisfy one relation. That's a 2-3 relation among the poles. So that explains. So for this reason, we expect the more exotic structure for this expansion of the thing. So for instance, returning to the planar basis, we can recover a pole, one of the poles R, as by placing a blade on the vertex 135 of the hypersimplex. So more precisely, this means E1 plus E3 plus E5.
Nick, there's a question from
Yes, please.
Atu. You can go ahead.
I was just wondering if there's some kind of a classification of which singularity we would call the physical factorization singularities in these generalized amplitudes, and what's a spurious one?
What is a spurious?
What would be a spurious? I suppose you have some spurious poles as well that would cancel in some of these expressions.
So for generic kinematics, I believe the understanding is that it's possible to write down an explicit collection of poles, and they're constructed explicitly from subdivisions of the hypersimplex, positroidal subdivisions, or rays in the positive tropical Grassmannian. I won't be going into detail there, but there is an explicit classification of the poles, and those are exactly the poles of it. So, okay, I mean, there's a way to do it. It's not, I mean, it takes some work, but there's a way to do it, yes.
And so can you also develop BCFW-like methods other than just using the scattering equations to compute these things? Can you develop other methods like BCFW?
Very good question. Like BCFW, I don't know of such a thing as that. I know. Yeah, I mean, if you take certain specialized kinematics, like restrict the kinematics to a very small subspace, then you can get exact expressions that are much simpler. The number of poles is much smaller, and you can construct it explicitly. But I don't know of any sort of anything exactly like BCFW. But yeah.
If I can just say something quickly about this. So as Nick was saying, all of the poles that he's showing here are physical poles in the amplitude. This fact that even the numbers of poles are different, even in these simple examples, reflects the fact that this amplitude is the canonical form of some polytope, but that polytope is not simple. And I think the sort of overarching question about whether there are BCFW-like or other ways of computing these amplitudes is really the question of whether you can, whether one understands the facet structure of these polytopes well. In the usual cases, there's an analog of BCFW for the icosahedron, which are these various classes of triangulations that make the projective invariance of the canonical form manifest. Those are analogs of BCFW. They're not Feynman diagrams, they're other things, but we can get those forms because we understand everything about the facet structure of the icosahedron, and in particular, how it factorizes into other icosahedra. I think an open question about the CEGM polytopes, and maybe even these newer objects that Nick is going to tell us about that are more is whether we understand enough about their facet structure to be able to do these recursive kind of presentations of what the form looks like.
Okay. Yeah, thanks, Nima. Appreciate it. Okay, very good, very interesting. Okay, so let me give more terms in the expression. It turns out that there are 48. The natural expansion of the amplitude has 48 fractions. So there are certain combinatorial objects that label these. So there is like, even though you have linear relations among the poles, there is a single expansion that is somehow most natural. And yeah, it is modeled on it's modeled on the face structure of a certain polytope. So that's yeah. So each diagram here corresponds to a vertex of this polytope. And in the case k equals 2, that polytope is the isosahedron. And there's a, so yeah, I mean, we'll see more of that. Okay, so more about k equals 2. Yeah, continuing the overview. So let's take a bunch of kinematic data indexed by mu's. So mu's here are just parameters. A priori, they could be complex, usually real, actually often positive prime numbers, but we'll leave them generic for now. And then the potential function can be rewritten in this compact way. In this, so what should we ask about this? Well, we can ask about, just supposing we were given just this from scratch, just this, we didn't know about amplitudes. Well, we could, let's look at the critical points. We found that, again, recall that we found that there's a unique critical point when n equals 4 and k equals 2, like that. And so that means that as mu13 varies, mu13 and mu24 vary, we get a map from CP1 into the torus quotient, into M0n. So we'd like to generalize this. Okay, and calling this root kinematics. Okay, so if we specialize the mu ij's to sums of alpha i's, you can see the notation alpha I up to alpha j minus 2. Then the potential function has the following simplification. It's just and collected around the alphas. Proposition that the positive parameterization of G2n is a solution to a differential equation. And it's this differential equation when you choose root kinematics. And you recover, and the argument is, well, you plug in the positive parameterization, and that gives you the unique critical point, and that critical point is where xij, like x1j, is equal to alpha I. So sorry, that should be just an xi equals alpha I. That's in the more general situation, we'll have xij equals alpha ij. But yeah, here is just shut your eyes to the j for now. Okay, we'll return to that a little bit later, but let's look more at root kinematics. So if we evaluate the amplitude on root kinematics, you can see that it simplifies to this thing that looks kind of like the canonical form for a simplex, maybe. It's if you expand, you get a sum over alpha 1, 2, alpha 2, 3, alpha 1, 3. Well, the amplitude itself, the collections here, you notice I put the isosahedron, the two-dimensional isosahedron down there. We measure index by pairwise non-crossing pairs. So you can certainly show this using say the CHY formulation, but let's give a combinatorial proof that on root kinematics the amplitude evaluates to this simple expression. Well, to do that is you recognize that these parameters are roots. So this is the motivation for the term. Here's how it works. Identify alpha j with the difference of coordinates xj minus xj plus 1. Then you see that the summands, you can identify the summands here with the Laplace transforms of simplices in the triangulation of the root polytope. So this is the convex hull of the roots xi minus xj for I less than j and the origin. So that is to say, it builds the M2n amplitude from this from the triangulation of the root polytope. Okay, so let's look at combinatorics here. Combinatorics of root kinematics. So we're going to label the poles specialized to root kinematics. Remember, we're labeling them by pairs of integers which are not cyclically consecutive. Well, in this case, this is cyclically consecutive. We're a priori, we're going to say that this is non-zero. Okay, so when you add, notice that 1, 5, and 2, 6 are crossing. Well, you can add them and replace that with a pair that is non-crossing, a nesting pair. And in general, you have two kinds of identities: a 2 plus 2 identity and a 2 equals 1 identity, depending on the adjacency of your ABCDs. Okay, and this has a completely natural generalization to higher K, which we'll hopefully get to see in the next little while. So here is again what 2, 5 looks like very quickly. I just put it here. Except we're taking a deformation where eta ij equals gamma ij plus 1. And this has the poles on a very special pentagon, a very special polygon, the isosahedron, where we're taking here the coordinates alpha 1 plus alpha 2 plus alpha 3 to sum to 0. So here is last time, to reiterate, here is what it looks like. Yeah, so we can put the poles in bijection with these alternating trees, and that connects to work of Gelfand, Grive, Postnikov, and another work by Postnikov and Corolla Mesherosh on subdivision algebras, just to name a few, triangulations of the root polytope. And here is, let's evaluate now the 6-point amplitude, again, on an integer kinematics. So these alpha 1 plus 1, but notice that there are linear relations, additive linear relations among the poles, like eta 1, 3 plus eta 2, 4 is equal to eta 1, 4. So that means that some of the poles are spurious. So the terms here, the 14 terms, will probably, and they will, be reduced in number. So there'll be some cancellations. And it's the following. We get 6 terms, assuming that alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is 0. We get these 6 terms. They are in bijection with the vertices of this polytope. You can see the red edges here indicate compatibility with the root lattice of type A3. So it is what it is. We get a cancellation of the spurious poles, and we're left with these six contributions. Okay, more root kinematics. If you evaluate on the positive parameterization, then you get this extremely simple form, which is well known from likelihood geometry in algebraic statistics. This is well known to have a unique critical point. So it is provides an example. It has maximum likelihood, or ML degree 1. Okay, we're switching gears on the next slide. So let me pause quickly one more time for questions or comments.
I have a question.
Yes.
Can you say what the polytope is for the k equals 2 general n here?
The polytope on generic kinematics is the icosahedron in a very, I mean, it's the icosahedron. If you mean if we take this deformation or just a general?
Yeah. For this deformation, yeah. I mean, I know that. Yeah. So
Yeah. Oh,
yeah,
sorry,
I'm asking
sorry.
what the analog of this picture is.
Sorry, Hugh, you hadn't popped up, so I didn't recognize you.
Okay, fair enough. But yeah, so yeah, it's. I'm asking how does this picture that you're drawing here generalize to higher n?
Yeah. So when we take the gamma ij plus 1 picture is very interesting. Leads to an interesting polytope when you just take a +1 deformation. I don't know if, I mean, I couldn't find it anywhere, but let me tell you something interesting about it, which is that it still has the same number of facets as the icosahedron. It has the same number by n choose 2 minus n facets, reduced number of vertices. But yeah, I mean, it's a sub-Minkowski summand in Loday's realization of the icosahedron. Yeah, I mean, and I generalize this polytope to higher k if we get time for it. Yeah, it's it's a Minkowski sum of n minus 2 simplices too. I mean,
okay,
just some facts about it. So
okay, cool, thank you.
Yeah, two. That is to say, a bunch of it n minus 3 intervals and 1 simplex.
Oh, okay, cool.
Okay, so switching gears. So the on M0n, we can introduce some projective invariance, but let's take a step back actually, and just start with pretending we knew nothing about M0n and nothing about positive parameterizations. Just define polynomials tau ij to be the following sums. For I equals 1, an arbitrary j set that equal to 1. Okay, and then we have the sum for tau ij. Then when they are not cyclically adjacent, define these 2 types of rational functions. The one is a cross ratio like thing of degree 1. The other actually looks like a cross ratio. And we'll see that they are both, of course, I'm sure you can recognize they are both, they map through actual cross ratios on M0n. Okay, so what are the relations among the UIJs? Well, they satisfy these very nice binary type relations. Were studied, I think, back in even the 60s and 70s by physicists, and then more recently by apologies if I'm forgetting, but by Brown, Francis Brown, and then again in physics by ABHY. So what you do is you take a UIJ plus the sum over all pairs KL that cross IJ, and that evaluates to just 1. Okay, and yeah, I mean, from this you can deduce that if you set, say, UJ to 0, UIJ to 0, or maybe that's a bad notation here. Maybe I should say a UAB to 0, then use CD equals 1 for all KL that for all crossing pairs here. So that's a weaker condition than the binary relations. So I'll generalize the binary relations to higher K as well. Okay, so here's how it maps through the X2n, or G2n mod C modulo the torus. Uij is just the cross ratio, the following product of minors: Pij, Pi plus 1, J plus 1, etc. And you evaluate on this positive parameterization, which is incidentally the root, the potential function evaluate, the critical point of the potential function evaluated on root kinematics. Okay, so that's repeated. I don't know if you can, there are the physics references going up. Yeah, so here's the example for just for 2,6, the two kinds of relations you can see there, these and the cyclic rotations. Okay, so let's take work in the U space. Then the worldsheet associahedron is the solution in the U space to the binary equations. Okay, we'll just make that definition, and we've given an explicit parameterization using the tau ij's. So we've solved the binary equations given an explicit parameterization. Okay, now for K equals 3. What we have is the following. We have to introduce a crossing rule, which has appeared in the math literature in various situations. So you notice here, oh, okay, so what's the rule? Take adjacent pairs. You check if adjacent pairs are crossing. Given a pair of subsets I1, I2, J1, J2, recall that's the usual K equals 2 rule. Now given two triples, you check that is I1, I2, J1, J2 crossing, is I2, I3, J2, J3 crossing. Finally, check if I1, I3, J1, J3, and the index in the middle, if the index in the middle are equal, and the boundary guys are not crossing, then you're in then you're out of luck, and the two pairs are crossing. Okay, so what you're hoping for, it's crossing provided that you get for any adjacent pairs, for either of the two adjacent pairs, it's non-crossing, or you have a crossing on the boundaries and the middle two guys are not equal. Okay, so you don't have to memorize this. It's not, I mean, we'll look at this combinatorially in a second. Okay, so examples of crossing pairs. But more importantly, examples of non-crossing pairs. So here in the, you can check, these are usual non-crossing pairs, but these two are the interesting ones, the last two. These are non-crossing because a priori 1, 5, and 2, 6 would be crossing, except that 3 and 4 are not equal. So that's a non-crossing pair according to the convention. Except this is not just a convention, it's what we get from out of the consequence of a generalization of the tau variables, the planar face variables. Okay, so we're going to define abstract binary equations. Then we're going to give a solution for them. So here we go. Take a triple. Yeah, and I should explain this notation. It says the set of all 3 element subsets such that the triple is not a cyclic interval like 2, 3, 4, 3, 4, 5, and 1, 2. So forget the n cyclic intervals. And then you have this rule. You said uj equals 1 minus product overall triples I, such that the pair is not in there, and you have to raise certain of them to the power 2. So you raise it to the power 2 if the two pairs I1, I2, I3, J1, J2, J3 are strictly interlaced. And we're going to call the, we're going to say that we're going to denote by W3N plus the generalized worldsheet icosahedron, which is the solution space in the U space to equation 1. So we'll give the 3, 6 the full list. Well, we have 20 minus 6 guys. Yeah, you can see that the squared appears in 2 places, for 1, 3, 5 and 2, 4, 6. The 2 pairs that are strictly interlaced. Okay, solution time. The planar face polynomials, these are going to lead to a solution of the binary equations for k equals 3. So what do we do? Let me check something. No. Yeah. So given we're going to define 1, 2j to be just 1. 1jk is a sum, the following sum over an interval. Tau ijk is, it would be a Cartesian product of intervals, except that we're asking that a be less than or equal to b. For instance, here's tau 136, that's just the sum. Tau 356 is more interesting. That has a single irreducible factor times a variable. So in this way, we're able to isolate the index I equals 1. So xij, where I equals 1, we're able to isolate that. Here's 468. Is what it is. And notice also that we can set, you can have a repeated index. The first 2 indices can be repeated. It's part of the definition. Now, what are the uij's? We have 3 cases now, not 2. I'll let you look at that for a minute, but suffice it to say that if the last index is n, then you have a degree 1 thing in numerator denominator. If the last 2 indices are n minus 1 and n, then that's what you get. If you have that the last index is n, you have 1 case, and if all indices are less than n, then you have a final case. So the key point is that you have tau ijk, and then another tau with the either the first and last or the first and second indices shifted. Oops. Okay, so we've checked. I've been able to check these relations and generalizations of the UJs for ridiculously high order in K just on my laptop. Found binary relations for as high as 510, Kn equals 510. The part I do not have yet is the corresponding rule for the exponents. Can conjecture, obviously, obvious conjecture is what it is. That is what you'll need to get the binary relations. Then we can define the worldsheet icosahedron correspondingly. Yeah, I think the exponent rule should be very nice. All right. So next we're going to show how to realize the taus and the uijks by how it maps through x3n. Yeah, so we'll take this weird looking compound determinant coming from nowhere, x nihilo, and yeah, then we divide by these 2 factors. Okay, so where does that come from? well, notice there are two cases. If ijk contains 1, then we don't change the minor. If otherwise, we replace pijk with this resolved minor, which is aijk divided by these two, the product of minors. That's what they look like in the case 3.6. So these are the only two minors that are changed non-trivially in the case 3.6. In the positive parameterization, here's what they look like. Here's the positive parameterization, and here's what they look like. 3, 5, 6, the irreducible factor is just the sum of 2, and the other one is, the other guy has 5 terms instead of the 6 that we'd see from the usual minor 2, 3, 6. Let's visualize the tau variables, the planar face polynomials. So we'll take a staircase, the staircase. We'll, what we do is start, you don't have to start at the top left, start from some vertex of a grid, and then draw rectangles such that there is an overlap of exactly 1 unit line segment going down. So we have a length 4 guy, length 2, 3, 4, 5 guy, but it has a single column in common, etc. I see I have just a couple minutes left now. So that's our planar face variable. Okay, I'll at least define what generalized positive roots are, and then it looks like we'll be out of time. So in the case k equals 3, what do we get? So to be clear, well, yeah. So what's the rule? Given a triple ijk, where we think of the ij, the variables alpha ij as simple roots of each is of type A, capital A, Dinkin type, capital A, n minus k. Right, then we'll take the sum, and it's the sum of these two positive roots. So alpha 1 with an interval is a positive root, alpha 2 with an interval is another positive root. So we can represent these on a grid. Again, on a grid. So for instance, the generalized positive root, according to this monster, is it's a slanted staircase, which I don't want to try to walk down. Okay. So let's see, why is this useful? Well, first let's look at the flip relations, and I'll try to wrap it up soon, in just a second. So what are the flip relations? You can see they interchange crossings and nestings. Let me conclude with root kinematics for k equals 3. Okay, so if we evaluate a planar basis element, A to J, where J is a subset, evaluate that on this generalized root, claim is that the potential function has a unique critical point, and that critical point is in the image of the positive parameterization of xkn. It has a very nice formula. In the case 2.5, again, it was this. It's even nicer in the positive parameterization, which is how you prove it. In the case 3.6, I think I give 3.6 next. Here's what it looks like for 3.6, and then I'll give the general kn expression on the next slide. It's this following thing. It's well known in likelihood geometry to have a unique critical point. We have simply it's a linear potential function, and we have k minus 1 times n minus k minus 1 alpha ij's, which are one more n minus k minus 1 times n minus k alpha j's, and you have some torus scaling here. But the unique critical point is given by xij, the positive parameterization equals alpha ij modulo the scaling. Yeah, so you can, let me run through the last slides. You can define a root polytope exactly as we did in the case k equals 2. Okay, it has n choose k minus n vertices. And gamma, if we restrict the generalized roots such that the total sum, when you have a cyclic interval is 0, then our kn has exactly our n choose k minus n vertices. May I have a couple more minutes? I think I'm on my last 2 slides.
Yeah, go ahead.
Okay, thanks. Here is a picture. Here's the picture of the root solid for type 2.5. Here's the headed version, and we're going to project down the diagonal through the center. And then we can induce the triangulation into the Catalan number of tetrahedra. And then we project again down, and we get a triangulation of the projected root polytope. Okay, theorem is that, well, I proved this for general k, but here in particular, since I defined the non-crossing relation only for k equals 3, I'll state it there only. Theorem is that this generalized root polytope admits a unimodular triangulation. For the experts, it's a flag triangulation, which means that the simplices are in bijection with maximal subgraphs, complete subgraphs, sorry. And we have that the volume of the generalized root polytope is a k-dimensional Catalan number. Now this is counted by standard rectangular k-by and Young tableau, I mean, among many things. If I had time, I'd show you the proof that if you evaluate the generalized biadjoint amplitude where all planar basis elements are 1, then the amplitude itself evaluates to the k-dimensional Catalan number. So yeah, I was able to prove a theorem that we conjectured with Freddy Cachazo in a previous paper that we have this evaluation. And I believe that is my last slide. Thank you very much.
Thank you, Nick. Are there any questions?
Yes, I have a question for Nick.
Yes.
So you mentioned this worldsheet as octahedron, right?
Yes.
So I was wondering if this object is supposed to describe the Biadjoint partial amplitudes. I mean, these generalized amplitudes. Like, for instance, the amplitude story street describes the CHY formula tree level, right? So it's true if I say that I can use this object to describe these generalized amplitudes or not?
Great question. Thank you. Yes, in fact, it is a modification of the generalized biadjoint scalar. So it's a new amplitude, which is close to the generalized biadjoint scalar. Yeah, it has some new features. Yeah, I don't know about, not sure about your other questions, but yeah. Did you?
I see, but for instance, have you tried to explore the vertex operators or something like that, or not?
No, but that would be an interesting thing to try for sure.
Okay, I see. And one more question is, can you do the similar analysis for gluons or gravitons, for instance, in this generalized story, or?
Again, yeah, that's an open question.
Okay.
That's a great question. It's open.
Okay, nice, thanks.
Mm-hmm.
I wanted to ask a similar question actually. In 4 dimensions, can you like take the 4-dimensional? So in this case, you took the CHY formulae and generalized them to CPK or whatever. Can you take something with the 4-dimensional twistor ambitwistor string formulae for n equals 4 and try to generalize them for CPK type worldsheets or something else with the 4-dimensional scattering equations or the twistor string equations, whatever, generalizing to some kind of Grassmannian type embedding equations?
I guess it sounds interesting. Maybe someone, I'm not so sure I have the background to answer that. Maybe Nima or someone else could weigh in on that.
So if I make a comment, I think the problem is if you try to generalize the G2n to GKn in the twistor string context in 4D, then you lose this, you lose the part that you mod out torus action, right? So we do not know such a generalization. So for like usual CHY or string theory, you have the worldsheet, which is G2n mod torus action, but literally in 4D, you do not have that mod torus action part. So this generalization, at least naively, won't work.
So I thought the problem was that there are no Koba-Nielsen type factors in the 4D ambitwistor strings. You couldn't even write.
That's similar. I mean, you could cook up such a factor by taking all the minor to some power.
I see.
But now you have no reason to ask those power to satisfy the analog of momentum conservation, which is given by the mod torus action part.
So I suppose the issue is in 4D, in the usual kinematics, you can trivialize null. Oh, sorry. No, why is there a problem with momentum conservation? You could still just.
No. I mean the analog of that, the thing, the exponent you want to put on this minors, right? So it's just I don't know such a natural. I mean I don't know how to write down such a generalization of the twistor string. I mean, clearly this is a natural thing to try, but
well, I mean, you could just imagine that you're. I think that just as you're saying, the ordinary twistor string is not modding out by the torus, and you just have the Park-Taylor factor. So you could imagine just integrating over GKN and not modding by a torus. I think that the question of what we're supposed to, what the amplitudes are supposed to be a function of is a little more, well, I mean, they can't be functions of lambdas and lambda tildes anymore. And also you need some, I mean, another thing you could try to, you could try some analog of some generalization of the Veronese embedding, but that also does not work so simply for mapping from higher K into even higher K. So.
Yeah. So might have something to, I mean, you can, there's an interesting thing you can do, two things with just what came to mind with when you mentioned Veronese embedding. So first of all, there's a way to characterize the image of the Veronese embedding in XKN as the critical point of the potential function with respect to a certain kinematics. I mean, a different kinematics has a unique critical point. So that could be, I don't know. I mean, that seems like something you could try. Another thing is just another instance where the Veronese the Veronese embedding comes in is that you can try to perturb the CGM, the potential function for XKN with a Veronese operator, in which case nice things happen. At least nice things I've just started to notice that, you know, just in the case small n. So I mean that's something else to try. But I mean, okay, that's all I wanted to say. So I mean, yeah, it seems that you get a simple polytope. When you have a simple polytope, then you're kind of more in luck as far as understanding the poles, understanding a closed expression for the amplitude, answering physical questions about the amplitude. I think you really want to have a simple polytope in that setting, and that's, yeah. So I think Hugh has his hand up for a while.
Yeah, I was wondering in the GER36 model that you were looking at, you wrote down some U equations, and they look like you could also get them from the cluster algebra structure on GER36, which is type D4, and you know, so there's a and the way that the exponents on U equations are just the compatibility degrees between the cluster variables. And is
But
that
he has 14 variables, not 16.
So I mean, it could be a cluster subalgebra, I guess. I mean, I'm throwing out two of the minors. So it's except that
The exponents look similar, but he has 14, not 16 variables.
wow.
Yeah.
So what's the connection between, like, is there a connection between the system with 16 variables and the exponents I would expect, and the system with 14 variables that you're looking at?
Yeah, I haven't tried to compare the binary equations. I mean, but probably there's something to explore there. I haven't looked at it yet.
Yeah, that seems really interesting to me.
And I mean, perhaps a related general question. So so Nick has something with almost everything perfectly paralleling the 2n story. So he has a simple polytope, he has perfect U equations that he can solve rationally with a positive parameterization. All of that's spectacular. But there's one thing which does not have the cyclic structure. And you said it quickly there, Nick, but for example, in the definition of compatibility that he has for higher K, there's a breaking of cyclic invariance in there, which we don't have for K equals 2. So at least so far, that seems to be an important part of your construction. Although you had been telling me about some other ideas you had actually related to what you were just mentioning about the Veronese operators, for example, that could give you a cyclic object. But anyway, those are sort of two differences, and maybe you could say something about cyclicity. But just to Hugh's comment, there's not only that the number of variables is smaller, but it also isn't cyclically invariant in the way that it would be in the cluster case. Yeah, but can you say something about this question of cyclic invariance? Because that's I think the only thing missing now in the sort of clean generalization of K equals 2.
Right. So, I mean, so this is like the okay. Let me think what to say. So I have at least two proposals for ways.
Actually, maybe before doing that, can you just go back to the slide just to? I mean, you've explained it to me, but just in case other people it went by quickly. Can you sort of highlight where this breaking of cyclic invariance came in your formula where you define compatibilities, in your slide where you define the compatibilities?
I have to find it very quick. Yeah, here it is. So the breaking, breaking of cyclic symmetry happens in the third line here, because you have to have a notion of which you have a notion of interior, right? I mean, if it were just a cyclic order, you couldn't decide. Yeah, I mean, there's some choice to be made here.
Right. So you have to decide who's on the inside when you have right. So you're And again, I have some candidate ways to
possibly complete this to a cyclic thing, but yeah, I wouldn't be ready to talk about that in detail.
Can I ask a more basic question to
Sure.
see if I understood? So there are two kind of themes to construct this sort of new combinatorics. One was you specialize the kinematics to be in a slightly special condition, and you get a simpler polytope. And then the other one is you worked on the worldsheet side, and then you took different UIJs and modified the binary equations. So are you saying that these are completely in agreement, or are these separate?
Yeah, I should probably clarify. No. I mean, they're yeah, it's probably too much. It would probably take a long explanation to show how the passage between the two, but no, they're certainly not equivalent.
Yeah, the thing that you get from generalizing the U equations is true for just completely general K kinematics. And so so you have some polytope associated with this sort of generalized binary geometry, but you say that there's a specialization of that polytope lands you on what you get from the special kinematics.
But somehow these
Thank you.
the generalized Catalan numbers, which is sort of the number of standard Young-Tableau of rectangular shape, aren't you saying they appear in both variants of your generalization? So on the one hand, you have a higher root polytope which has volume equal to this generalized Catalan number. On the other hand, this Peterson-Piliavsky-Speyer result also has simplices that are given by the number of standard Young-Tableau of rectangular shape. But you're saying even though they have the same number of sort of they have the same volume, they are different generalizations.
So yeah, so in fact, what happens here is that when you evaluate both, you can, I mean, the set of minors, you can evaluate the same guys on a special kinematics, very degenerate kinematics. On this very degenerate kinematics, the two potential functions coincide, and the result computes only the volume of the object. Of the generalized root polytope. But I found my result says that you can like do a second there are two different compactifications of this thing. One of them by adding in either all minors or these new tau guys. One of them lands you on the thing we know, the XKN story, and the other one lands you on the non-crossing story.
Is it an accident that this non-crossing story also has this generalized Catalan number appear?
No. I mean, no. I mean, the isosahedron in this story is dual to the non-crossing triangulation of the root polytope. So I mean.
Okay, but so you have two different ways to get the same simplicial complex. One is to specialize the kinematics, and the other one is to change the binary relations in the U variables. Is this do they give you the same simplicial complex?
Well, okay. I mean, I think this. Let's see. In the one case, I'm not sure which. I think I've lost track of which the two guys we're comparing now, but
one of them is the one that gives you this higher root polytope, and the way I understood it is this: you specialize the SJs in a particular way.
Yes.
And the other way is you take the U relations and then you modify them in some way. So I think there's two different ways that you talked about.
Yes.
Of varying the K equals 2 case.
Yes. So yes. So
you're telling me that they're different generalizations, but I'm seeing the same numbers appear.
No, sorry. Then I lost track. I mean, they're yeah. If assuming I think we're talking about the same objects, then yes, they are equivalent realizations of the same thing. But we just have to be careful. I think we need a longer discussion to make sure. we
Okay,
get-
okay, yeah, maybe now's not the time. Okay.